Great. Well, thank you for having me here, and thanks for the nice introduction. I'm going to talk today about video understanding for skill learning, and I believe this is an area, as we'll see in a minute, that can appeal both to kind of directions in robot learning as well as directions in pure video learning, even before robots involved. So that's it's going to be about understanding skill by humans. And so when we think about skill in video, what are we talking about? This can be things from everyday mundane things that you're just trying to get done to more aspirational things like having a beautiful pass in soccer, or when you're listening to your friend play a touching piece of music, or you're watching your bike mechanic fix your bike, or your brother is fixing one of the family's favorite dishes. You can see all these little glimpses of how human skill is on display and just how rich it is, as we'll see in a moment, for video understanding. And so to kind of motivate why we should care about understanding human skill in video, what happens if we have that capability? So two big areas that are going to be transformed. One is robot learning. So robots that are built to operate in human-centric spaces, to move about, to manipulate objects, they stand to learn by vicariously through human experience as seen in video. So robots that can learn by watching people to then have their own interactions successfully with a lot less physical experience of their own. This is the vision. And on the flip side, in terms of augmented reality and mixed reality, it's very exciting to imagine how a machine that has perfect perception of, say, my first-person visual experience could give me just the right assistance at just the right time. So knowing what I'm doing, seeing my activity, for example, maybe here I'm trying to do some task, some do-it-yourself task, then giving me just the right advice based on what I'm doing. And I think this is a really exciting possibility for functionality, but of course, just like my previous example in robot learning, it demands understanding human skill at a really fine-grained level in video. So let's unpack that second case just a bit further to imagine, what does this future look like in terms of assistants in AR, MR that are based on wearable devices, say your smart glasses, that can see what you're seeing, hear what you're hearing, and then provide you that extra help. And I'm going to play this video to show you what it might look like. So right now, if you're trying to learn something new, like maybe you're trying to cook a new dish, you might go back and forth to your phone and try to figure things out. What if instead you had this heads-up experience through your smart glasses where an agent is watching your progress, telling you when you're done with any given step, like we'll see here, and giving you kind of contextual tips that are grounded in the real-world physical experience that you're carrying on. And in a different front, but related kind of function, imagine learning a new skill like in a sport where you want to understand the fine-grained feedback about your actions, like, oh, how are you holding the tennis racket? How is the execution of your swing? Such that you could pull up videos that are most relevant to help you in that moment, or even have kind of novel 3D visualizations of your own performance that will, in turn, help you get better. So this is motivating application world that I really think we can achieve as we build up some important perception technology. And in doing this, what we're particularly interested in is first-person or egocentric video. So of course, if you're talking smart glasses or even the first-person perspective, as we try to vicariously have the robot vicariously experience our own visual world, then we have this wearable first-person perspective that's no longer kind of nicely curated, well-taken videos that someone thought to take, but really just uncurated, very long-form video that, importantly, is driven by this agent's goals, their interactions, their attention, and the environment. And has these wonderful properties in the video that we can both grapple with because of the new challenges, but also take advantage of for getting this window into first-person perception. All right, so for any of those kind of big directions that I just motivated, there's two key problems that I want to isolate in this talk. So the first one is, if we're going to have this kind of skill understanding, we need to understand the subtleties of human activity. So it's not enough to know, oh, which sport are they doing? We have to know, or which instrument are they playing? We want to know exactly how they're using their body with respect to objects, and how they're executing different steps of a task. This is really a fine grain or subtle representation of human activity that we today lack. And then the second key challenge I want to talk about is capturing the link from third person to first person. And in shorthand, I'll call that from exo to ego. So exocentric to egocentric. Ego here is on the top. It's a wearable kind of first person view. And exo here is on the bottom. And in skill learning, this matters a lot because we translate the visual, what we see from the third person as we're watching as someone demonstrate, as we're watching a coach, we need to translate that onto our own bodies and our own point of view. And so being able to move fluidly between the egocentric and exocentric perspectives is actually essential for skill learning. Okay, but of course you can imagine how hard this will be because these viewpoints are dramatically different. Now I can motivate this ego and exo link in terms of coach and student or teacher and student here, but the same goes in robot learning, where we can imagine cameras that have seen people do activities from the robot's point of view and then trying to map that onto maybe your dexterous robot's own activity. And the analogy carries over into cognitive science, where we know from developmental learning, infants are watching their caretakers exhibit different activities and then mapping them onto their own experience. Okay, so this is a fundamental link. Visually, it's going to be challenged to overcome this gap, but we need to be able to study this for understanding human skill. So before I get into some of our modeling and capability contributions, let's talk about where we are in the field as far as data for studying skilled fine-grained activity. When we were looking into this in recent years, we see that on the one hand, activity understanding has been focused on a granularity that's much coarser. So things like, think kinetics and other influential data sets that push the frontier of activity understanding, but do so at a level of abstraction that's things like, oh, are they mowing the lawn or are they riding a canoe? And there's similar kind of level or lack of detail in today's video language models as well. So we're concerned about the coarseness in the representations and the data. And then when you think, especially in the multimodal setting, then the kind of collections that we could do so far have been rather lab-centric, right? We have a lot of control for camera placements or other instrumentation. And so, this comes at the cost of in the wild visual observations for human skill. And so this brings me to give you a snapshot of some work we've done over the last several years together with all the folks you see on this slide from different universities around the world. And we formed a consortium. In fact, we formed it going on 4+ years ago called Ego4D, looking at egocentric perception in 4 dimensions, both space and time. And the geographic diversity of this group is a bonus in addition to kind of the intellectual firepower of the group that you see here as well. Because by coming together to create this consortium in our effort called Ego4D, we were able to get cameras into the hands of people in these various locations, some 75 different worldwide locations, to get the wearable first-person experience from many different walks of life. So people aging from 18 to 84 years old, balance of different gender, indoor, outdoor activity, in the wild, kind of what people are doing in their daily life activity, both in private, solitary activity, as well as social ones, or in private or public settings, even interacting with animals. And so the excerpts you're seeing here are tiny glimpses from much longer clips, that each of which span up to an hour in length. So nearly 1,000 participants then contributing this kind of video to form a order of magnitude leap in scale and diversity for first-person video. Now, I've already alluded to kind of the diversity from age and gender and location, and also background. So we know that what we can expect is people's visual experience will vary depending on what they do in daily life. And so one way to capture that is by here, self-reported occupation. And you can see kind of we've broken free with Ego4D from the world of graduate students to include all these different kind of domains like coffee shop worker, carpenter, mechanic, farmer, and many others. Okay, so then that brings me then to our latest effort with this consortium, which is called Ego-Exo4D. And a moment ago, I motivated ego and exo as 2 important perspectives. Ego, like you see here on the left, capturing that first-person experience, the attention, the kind of manipulation-centric viewpoint. And on the right, you see several exo cameras that are in the Ego-Exo data set simultaneously captured, and these have their own value because of the ability to capture the full body, its pose, and the scene context. And so the Ego-Exo4D collection is, if Ego4D was about in the wild, everything you do any time of day, Ego-Exo4D is more focused specifically on skilled activities. And so we had 740 subjects, more than 1,000 hours of content, and heavy multimodality that I'll show you in a moment. The domains of skilled activity that we captured are shown here: cooking, music, repairs, health, sports, and dance. So things that, again, are from daily life. Oh, I need to fix this, to or I need to want to cook this, to kind of specialized skills that people are picking up, whether in sports, dance, or music. You also notice that these activities have some aspects of procedural activity and some aspects of physical activity, and of course those two can overlap. Now, what's really cool about the people who contributed to this data, as in wore the cameras or provided annotations, is their diversity in skill. So we made sure to recruit people who had different levels of skill in the given activities that we're capturing, as well as experts in each domain who we'll see later in the talk provided commentary about the quality of the action that people were exhibiting in these videos. And so that ranged from professional soccer coaches to groups of dancers from Chinese folk dancing or salsa dancers. So people with a lot of professional experience looking at the content here to give a rich annotations about skilled activity. And then the final thing I want to stress about Ego-Exo4D is the multimodality of it. So because we have these calibrated and time-synced multi-camera views, all the cameras are reconstructed, state-of-the-art. Here you're seeing a point cloud of the state-of-the-art reconstruction from these views, the cameras themselves in white, as well as the Ego camera shown here in green. And that red bar is the gaze direction that's also extracted from the ARIA glasses we use to do this capture. So what's exciting when I look at these visualizations to me is having now dynamic activity firmly grounded and available in the context of really the 4D environment. So the 3D structure of the environment and this dynamic camera within it. And this is really a new way to study human activity in video that we can do now at a scale and precision we couldn't do before. So with these data sets that the team has put together, both Ego4D, Ego-Exo4D, we came up with benchmark tasks to help guide the community's research and progress. And so here I'm highlighting them with icons, things from episodic memory and question answering to body pose extraction, proficiency estimation, and correspondence across the widely varying views. And so these are public challenges that have now been going on, offered for going on 3 years. And they continue to be offered, continue to grow in terms, as you see on the right here, in terms of participation, which is very exciting for, measurably pushing up the state of the art for these egocentric challenges. And in fact, for anyone interested here today, I encourage you to take a look. There's the array of challenges I just highlighted open and available on both these resources that'll culminate at CVPR this summer, and the challenge goes on until May 19th. So methods you have for activity understanding, for anticipation, episodic memory, question answering, video language, there's kind of something for everyone, and here from the egocentric perspective. So check it out if you're interested, and please participate. All right, so then I've told you about data resources that'll help get us off the ground for some of the things I want to show you next. And I'm going to zoom in on that second challenge, which is linking ego to exo. And there's 3 examples I want to show you. One, we'll first look at learning view-invariant representations. I'll talk briefly about cross-view translation, and then I'll show you a new idea for viewpoint selection. Okay, so this is where we're headed in sequence next, starting on the left with the view-invariant representations. So we're interested in being able to have visual features for video frames that are view-invariant, because we wouldn't like to be tied to a particular camera view. Now, of course, I've already kind of hinted at how challenging this might be, because when you want to understand that the activity is the same at a very specific point in the activity, whether you're in an ego video or an exo video, you're contending with a very wide camera change. And in fact, the thing that would most cluster features or relate features from either of these views is the viewpoint itself. Like if you took an off-the-shelf good video frame representation for the top video with pink and the bottom video with green, you know, the thing that's most similar about them is not how are they using the racket, but what camera took the picture. Of course, we want to get rid of that. We want to have representations that instead align according to the phase of the activity. So I'd like to know that when for example, here, if the racket's outstretched in the ego view, I need to know how that relates to the same action in the exo view. And so our study of this, what was new is to, you know, not just learn a view-invariant representation, which past work has certainly considered in different forms, but to do so even when we have unpaired, unsynchronized training data. So Ego-Exo is a great resource that does have some of the synchronized data, but the wide wealth of Ego and Exo video is going to be unpaired today, just piles of content of relatable topics like tennis or something else. And so that was the insight of our method, is to be able to do this through an alignment mechanism where we take two video sequences of a related action. And then during training, we're saying that we want to learn a frame encoding that minimizes the alignment cost under some dynamic time warping loss here on the right-hand side between any two relatable sequences. So that would be an encoding that's going to then reflect the context of this broader activity. And furthermore, we have two aspects that we enhance. One is object-centric encoder. I said that not a lot survives between the ego-exo view shift, but the thing that will be shared in these manipulation activities is what the hands and objects are doing. So we surface to the representation, not just the global frame, but also the hand-object interaction region as input. And secondly, we introduce a self-supervised contrastive regularizer that allows us to take these two sequences, the ego one, the exo one, like shown here, and then say that the cost of aligning those two should be less than the cost of trying to align instead a temporally reversed version of one of the original viewpoints. So that's what's shown in the bottom row here. So if you were to reverse these frames, even without knowing anything further about any labels on this video, we should know that the cost of doing that alignment would be higher than aligning against the original true direction of the video. So we put those things together. We tackled some fine-grain activity data sets that we could match up in terms of activity relevance, like, you know, on the bottom right, different videos from UPenn, and our own collection of Ego video for tennis, or on the bottom left, pouring. And keeping a note is these are videos that are unpaired to the model and during training and contain different people, different environments. So they're only loosely relatable, but the alignment mechanism will overcome this. So what happens when we learn this embedding? Here I'm showing you two original unaligned videos. Both are breaking eggs. It's actually a different person doing it in each case. And they're not time aligned. So the egg reaches the hand at a different point. The egg cracks on the side of the bowl at a different point. But if we learn the embedding I just described, then we get an alignment like this, where you can see that the moments, those key moments are indeed aligned. What I'm doing here is taking the nearest neighbor for the ego frame in our embedding among any of the exo frames and playing it in time synced way. So the automatic syncing is based on the alignment in the embedding space. And this is great because it means now you have an encoding that is doing that representation based on phase of the activity. So you can see here on the T-SNE plot of these projections for each of the frames, each dot is a frame, and they're color coded from darker to lighter according to time.
Just give us a second. We lost your voice.
Oh, okay.
Please.
Still problem?
So here online, we can hear you. Must be some
Okay.
local problem.
Okay.
Yeah, we're back. Sorry.
Okay. Can you hear me?
We can hear you now.
Okay, good. All right, I'm not sure how far we're at, but I'll assume we're still okay to continue.
Last slide, I think that's where we lost your voice.
Okay. All right, well, I'll continue from here. So talking about the embedding, showing that, okay, once you learn them, now you can align based on the phase of the action. Here's another similar example, going from the top unaligned videos as input to the bottom matched frames according to these embeddings that start to line up the first person perspective of the exact part of the action to the third person. And I hope you can imagine, why this kind of building block will allow us to do, move towards the kind of things I motivated earlier with skill learning and relating the actions of a coach to the actions of a learner. And of course, we've quantified how well are we doing so far against things you might do alternatively. So in particular, self-supervised learning with paired ego-exo data, as folks have considered before, like time-contrastive networks and others, as well as alignment-based representations that have been devised not for cross-view analysis, but for feature learning and our relevant baselines. And overall, some really good promising results against the different baselines, data sets, metrics. Okay, so then in Ego-Exo Link, I've been motivating and say, hey, let's wipe away the differences so that we can just think of this as action that we understand no matter what the viewpoint is. But we are also interested in capturing the link for the sake of translation, even view translation. So imagine having the ability to see what it would look like from the eyes of the person that is in an original video. So on the left, this exo view, can we hallucinate or create, map, translate the video in terms of how it would look from their perspective? And that's the video on the right-hand side. And we call this the exo to ego cross-view translation problem. And to do it, you really want the model to account for the viewpoint shift as well as this lack of complete shared visibility in the two views. So some things will never be visible in one or the other. And we've been developing models for this. The results I'm showing here, our results are in the right-hand column, are for a diffusion-based model where, like the method I just showed you, we also find it effective to condition on the extracted hand poses. So a twist on what I showed you, so extracting the hand poses and conditioning on that with the diffusion model trained here to go from the exo to ego viewpoint allows us to get the synthesis you see on the far right from the inputs in the left column, which are all exo, to our result on the far right. And in between, you see the ground truth, the second column, as well as multiple baselines like pix to pix, HT, vid to vid, and others. And so this is an initial step where we're getting some progress for being able to make this hallucination or anticipation and accounting for a very dramatic viewpoint change. Okay, so next on the front of Ego-Exo and just establishing this link, I wanted to show you this brand new work we've been doing on viewpoint selection. And I'll motivate in terms of instructional video. So I think instructional video is such a fascinating domain for video understanding today, and certainly highly relevant for what I've been motivating so far for human skill. Because here you have, say the wealth of a data set like How to 100 Million showing thousands and thousands of activities, people instructing, people showing fine-grained skill, and even in a multimodal manner, because they'll speak about what they're doing, like we can see here.
Just scoop out some dough and pop that onto our baking sheet lined with parchment paper.
So you have this great video language resource focused on human skill from all parts of daily activity and beyond. So it's a fascinating domain for what we care about here. And the part I want to zoom in on is the notion that if you watch any good instructional video, you'll often see they have what we call a varying view property. So by that I mean, it's not a static camera giving you the feed. You kind of see from some number of perspectives the content over time. So it started looking close in like here on whatever she's cooking, and then maybe it zooms back out to an exo-like view when she's speaking or when she's reaching in the environment for something else. And this is standard because why? Well, to best understand the content and focus on the right thing as a learner seeing this how-to video, you want that viewpoint control. So how is it done today? Well, it can be done by and large through post-capture editing. So if there are multiple cameras, sequences captured, and then choose between them manually at any given time point to create that kind of stitched varying view video like I just showed you. So video editing is one way, or even depending on the domain, just active camera work. So maybe all views are not captured, but the camera is placed over time where it's going to be most effective. And the thing about this approach in practice is, of course, that it's time consuming, maybe even tedious. It takes a lot of manual effort to select these views. So our idea is to explore, can we automatically select the sequence of informative views to make a view varying video? And it's good to call out, the relationship between the problem statement I'm just about to go over with you and a couple other domains. There's been past work in automatic cinematography that's very inspiring. It tends to look at specific domains, say people giving lectures, and often with kind of heuristics, and there's challenges there in being able to learn an approach. And another domain that you might think of when we say view selection is next best view or active perception, certainly in robotics, where we want agents that learn policies for how to move their own cameras. And you can relate to that domain as well. Of course, the difference here is we're trying to maximize for human understanding of the video as opposed to, agent navigation or agent action in the world. So let me give you an intuition for our approach. The main challenge we're going to address here is that we want to select views over time in a novel video. We don't have best view labels. So a luxury would be if we had many, many edited videos of multi-view content and we knew which view was the best among them so that we could train in a supervised way. But we don't have that. And so kind of our insight is how to overcome that in the training. So we're going to say we have an instructional video that's captured using multiple cameras. Here I'm actually taking these clips from Ego-Exo. So you have an Ego camera from the glasses on the top right, and then here are two of the Exo views shown on the bottom, and this person's repairing a bike. And so given those multi-view captures, we want to decide at every time interval which view to shift to. So which view should we be presenting as the one to watch? And so here's our idea, how you could supervise this without direct best view labels. And we're going to do this through language. So here's our task. Again, given those videos, we want to select the best one, but without manual labels during training. And the key insight is to use language in the following way. So what we do have, in fact, from different data sets, including Ego-Exo4D, is narrations. So spoken or written content about what is happening in the multi-view video. And importantly, it's view agnostic. So there's a ground truth narration that says what is happening in this whole video scene. And so what our approach will do on the right-hand side is to, during training, look at every view independently and caption it with state-of-the-art captioners. So for example, view 1, and the captioner might look at that view and produce, the person holds a rear wheel with both hands to inspect it. View N, going on the right, maybe the captioner for that view would say the person holds the rear wheel with his right hand, and so on. So you do this independently for each view. And meanwhile, you have in the background this ground truth view agnostic narration about the entire scene, which in this case is the person inspects the rear wheel with both hands. And now from the inferred language alone, comparing that against the ground truth, we could score them to say how aligned they are. And the more aligned they are, the more it means that that source individual view was adequate to capture the entire information of the scene. And so that's what you see at the bottom. Maybe the first one scores highly, the middle, and the last not so much. And that's the signal that the view itself produced the language that's most aligned with the view agnostic multi-view narration. And so what we're doing here then is amassing pseudo labels. So for all the training data, we can do this, having no best view labels, but having these narrations in language. And now we can have these pseudo labeled instances now of multi-view video along with the views that seem most informative for the full semantic content. So breaking that down a little bit further, then there's two main parts to the approach. We'll have the pseudo label I just described. And in fact, we use multiple captioners from the literature in order to kind of smooth over, any noise between them. So each of them produces a ranking of the candidate views, and we'll use some rank aggregation to come up with our pseudo labels. And then on the bottom there, the best view selector itself has two parts. One, a classifier that's trying to classify for the best view. So you'll take a multi-view input and then learn to encode and decide which one is best. And we found it useful to do this with a loss on the right-hand side here that is the min over all cases, trying to give some flexibility to what is easiest to learn. And then we also found it useful to add an auxiliary loss for relative camera pose prediction. Because if you think about it here, if we completely lose the view sensitive information, we won't be able to do the task. So we kind of enforce the maintenance of the ability to predict relative camera poses so that we don't wipe away the view information that is actually significant in this task to be able to know which view is more informative. Okay, so here are a couple examples. On the left, you're seeing the input, the videos. That's all we have at test time, no language. And this is from an Ego and Exo view. And on the right is our output over time. So think of this as our version of the auto-generated edited video for which views to look at over time. And what I kind of noticed in this example is as they're interacting with objects in the environment, we often get the ego view close up. And then as they move around the environment or switch stations, we often get the exo view and see that broader perspective. So that's one example. Here's another one from Ego-Exo4D with rock climbing. On the left are all the input views, and on the right are the ones that we're choosing over time, just like before. And you can see things like the exo can be informative, kind of looking at the route to plan. And then ego, as we see the person reaching for certain grasps. And then the exo looking at big body motions like here where they came down off the wall. And we've found different ways to quantify how good is this selection and ways to compare to things you might do instead. One of the best things you might do as an early baseline is to look at how well is the body captured in any view, the hands, the objects, the body, and these are good things to try, but still not as strong as what we can get from this learning approach. And we also compared to baselines from the literature about camera direction, as well as another simpler ways to use the captions themselves, in particular, saying, oh, maybe the best view is the one that produces the longest and hence most detailed caption. So we got some good results here. I'm showing them from Ego-Exo, also a data set called Lemma. And not shown here is the human study where we had people look at the outputs and give judgments about which is better, which is, of course, ultimately very important for this kind of task that's about creating videos for human consumption. Okay, and of course, this is early steps for us. It doesn't always work. One of the common failure modes, here's an example where these two clips from some salsa dancing in Bogota from Ego-Exo, this dancer is shown from two different perspectives with similar ground truth narrations, but we would choose different viewpoints for either one. That's what happened in this case. And so it suggests kind of thinking about one, as we're trying to do in the loss right now, the fact there'll be some ambiguity or related views similarly good. And two, thinking about imposing kind of higher level smoothness or maybe more elaborate than that kind of constraints about the trajectory of the selected views over time, which right now is not in place. It's simply every chunk, every clip making a decision. Okay, so I've talked all about Ego and Exo. I talked about the data from our Ego4D work to the Ego-Exo4D, which is more recent. And then I talked about different ways in which we're looking at how to bridge from Ego to Exo. And now I want to talk about that other challenge for the remainder, which is about understanding fine-grained human activity. And there's three aspects I want to share. Some new work, we're looking at interaction prediction, knowing what people are going to do next in a 3D environment. Then I want to show you what might be the closest aligned to that sort of vision I set at the beginning about the assistant that's helping you learn new skills. So I'll talk about generating actionable feedback from video. And then finally, I'd like to touch on activity task graphs. So leveraging the structure we know exists among activities, especially fine-grained procedural activities. Okay, so let's look at this first, interaction prediction. So if you look at the literature, there's a great body of work that keeps growing on anticipation or forecasting in activity space. And the whole idea is, rather than just saying what you see now in the video, can you anticipate what's going to happen next? And so this is taking different forms. It's studied in egocentric, but not exclusively in egocentric video. And you can imagine like the power of having this both for a robot or for an augmented reality system where you either, you want low latency or you want to make decisions based on what's likely to happen next before it happens. Now, what we notice about existing techniques, including our own work in this area, is that they have an emphasis on what's happening. And that can be viewed as rather coarse, and they lack the where and the how, which I'll explain more in a minute. And importantly, they're largely 2D formulations. So really, these are processing videos as little 2D frames that we just keep observing over time, kind of removed from the physical 3D context. And this, we think, is really a shortcoming. What we want to be able to do is ground the human activity, as it often is, in the 3D space. So meaning the fixed environment, as well as the objects in that environment that are present at different locations, to ground the human activity with those things. And this would elevate activity understanding to truly a 4D kind of process. And in particular, beyond declaring what is next likely to happen, like, oh, next I think they're going to pick something up, we want to say where, so where in the environment in 3D is that likely to happen, and how, which for us means with what kind of body poses are we likely to experience given where they're trying to go and interact next. So in this screenshot here, we'll see in motion in just a moment, but what this is showing is the problem statement and some of the data we'll be looking at, where in the dark pink, you're seeing what you would observe of the person in the video at first, and then the lighter pink is what you're asked to anticipate. So which is where they'll be next in the environment, and with what body poses will they be interacting. And you can also see the 3D boxes here for objects that will need to be detected to help us learn these, the objects help us learn the patterns of this activity over time. We call this fiction, and it's for 4D future interaction prediction. So here's a sample. This is from Ego-Exo4D, where we're observing the person interacting at this part, and you can see the video inset at the bottom right. So we observe over, reasonably long time period, and then we anticipate over reasonably long time period. So today's anticipation models typically look seconds ahead. Here we're looking up to a few minutes ahead. And what these blue color is the ground truth future pose, and the pinks are samples of the predicted future pose over this time. And you can see that we're starting to predict these interactions of where the person will be and how they'll be interacting with their changed body pose. Which of course, these things are so linked, right? Because the structure of the 3D environment, where the objects are, where the big surfaces are, guides how you need to use the body to do your interaction, whether you're reaching for a cupboard or bending down to open this one, or reaching into a sink to do this, and so on. And you can see that as the time progresses, then the anticipated actions become the current actions, and we keep anticipating forward in time. Okay, and so the model that we're using to do this is 4D. So we're able to observe the the video as well as the poses over time within this 3D environment. And we're kind of encoder decoder. So we're encoding from there and decoding out to a voxel grid that says whether the interaction is going to be present and which location, like where it's going to be present, as well as a distribution of body poses within each of those voxel grids. So that's our output space, and here I'm visualizing it through these videos. Here's one more from the bike mechanic repairing the bike. You can see them starting the action, and then we'll start to anticipate where they'll be needing to go next and with how they'll be using the body. Okay, so this is our recent work kind of trying to, as I mentioned earlier in the talk, trying to bring activity understanding really into a 4D context, where 3D work meets the 2D kind of video activity work, to think about human action in physical spaces. So finally, let me tell you about the second part that I wanted to share on fine-grained activity. And this is our new work. Actually, both of these two that I'm sharing are at CVPR this year. That's about generating expert actionable feedback from video. So here's the goal. We'd like to have a video as input and be able to provide meaningful commentary and critique as output. So what's really interesting about skill learning and is where it needs to take us in terms of not just saying what we see in the skills, but also how would you fix them? So coaching, it's not enough to declare, oh, I see what you're doing and here's your body pose. You actually want to do that, but also say, well, here's how you could fix it. And I think this is very interesting from the vision point of view, because this is a fine-grained understanding challenge to be able to say something meaningful that's like the delta of what needs to happen. Okay, so like in my slide here, on the left, this is an input video, just a frame from an input video, 1-2 frames, and say that was our input. Then the output should be a demonstration video from an expert that shows how to correct the particular mistakes that that person was making. So suppose that the problem they had here was they were taking big steps, they lacked body control, they need to slow down, have better body control. The system that we want to create would give that kind of language-based feedback as well as visualizations through video or post sequences that say how to make the correction. Okay, so that is the goal. And what I want to call out is that it is fine-grained, right? Because if we say, okay, we look, if the system looks at the video and say, well, it's not perfect, this isn't the best skill, and just returns a video of someone doing that same thing, but with really good skill, it's not actionable and it's not a learnable piece of feedback unless it's closely related to the original input. So in other words, we really need to zero in on what's the delta. So to help support this work, I'm going to turn to a part of the Ego-Exo4D data that I think is really cool, because we had hired experts. I mentioned, these college coaches, professional athletes, and so on, who watched all the video and gave commentary like you see here. Let me play an example.
Great footwork. He's using a dribble to set up his footwork and his shot. Stepping onto that left foot, bringing the ball up. Love that his eyes and head are up. He's already knowing where he's going to go.
Okay, so in a sense, what I just described you as our goal is to automate this, right? Wouldn't it be amazing if given the video, we could say meaningful, precise things about what would make it, what is good about it, or what could be better? But we do have this data, and that's going to help us do some training to build an expert actionable feedback system. So let's do that by getting to that notion that we would like to create, in this case, really pseudo-label paired data that shows an input imperfect demonstration against one that corrects its imperfections. So here's how we create such pairs. We've got the video, we've got the expert commentary, which are these extensive language descriptions, free form about what's good, what's bad. And we use language models to condense those commentary bits to the essential summary and also extract automatically what are the parts of the body that are being referenced in that particular part of the feedback. Like, is it the legs, the arms, any of the physical aspects that are called out? And then we can start to pair up instances that are talking about the same part of the body, and which one is, I guess, the negative and one is the positive that corrects that mistake. And in fact, we make sure they're as aligned as possible by doing some temporal alignment across, searching across samples to find those that have the greatest temporal alignment along the pose sequences. So now you have data that consists of the video, the commentary, which is the T for text, and the corrected video, which is the expert video that is very much like the original source video, but fixes the problem that it had. Okay, so we've come up automatically from the commentated video with this kind of paired or triplet training data. And then we build a model that will use these samples. So here here's one example of what I just described, like the original video, someone who's learning, the expert commentary condensed for it, the shooter's using 2 hands instead of 1. And then the pulled expert video that automatically is retrieved to be its partner, I guess, to show the improvement of exactly what's needed to be different there. And so we're doing this across domains. Here are 3 domains: basketball, soccer, and bouldering. So this is all training data. And then we build the model to convert. It's basically exploit the strict capabilities of a large language model, convert all the modalities to tokens. So whether that's the video or the body pose estimates or the text itself, and then use them for the different tasks I've described. So breaking down the different tasks, one version is we push in the video and we infer the language commentary for it, or we're pushing in the video and the commentary or inferred commentary and coming back with the selected video that shows it, or similarly coming back with the generated pose. And so here's an example of the actionable feedback that gets generated. The input video, the body's too straight when hitting the ball is the thing to notice. And the commentary our system generates here is in the blue box, where it says the player's stance is too straight, which prevents them from generating the required power and control on the ball. And you can see in this case, this is pretty well aligned with what the ground truth commentary was from an expert. And then here's the expert video retrieved. So if this was the thing you need to improve, shown on the left, here's the way you might do it to improve it, shown on the right. And again, it's not just any good expert doing this particular drill, it's the one that most aligned minus the error from the guy on the left. And the corresponding body pose for it. So this is what allows actionable feedback. Here's one with the basketball shot. You can notice they're jumping straight, they're not bending the knees much, so this needs to be corrected, and it comes up in the commentary we generate. Shooter needs to jump with the knees bent higher to generate more power. And then here's the example that comes back. Again, this is a retrieved example to say, here's the way to do it to fix that mistake. Great, and we studied how well this is working, including with human subject tests. So where raters, human judges would rate the results in terms of how well they show actionable feedback, whether we're doing the commentary generation, the video demonstration retrieval, or the pose generation, compared to other things we could do with video language models, including those that are oriented towards pose specifically. And the results are encouraging. So I guess you can see here from the orange bars, the preference for the expert commentary or expert actionable feedback we're generating. Okay, and we had some AV things earlier on. So for time to make up that time, I'm going to skip to the end here so we can have some time for discussion and questions. This was where I would point you to our work on task graphs for video understanding, fine-grained video understanding, and we'll close in one slide here at the end. Not this one. One moment. Okay. Okay, so good. I've shown you some of our work towards building AI models for skill learning through video understanding, and I emphasize these 2 main challenges: fine-grained activity in this latter part of the talk, as well as linking ego and exo perspectives. And I also shared kind of an overview of some of these new data resources that we've been involved putting together. And I'm highlighting the first authors here at the bottom. So thanks very much for your attention. Would be really happy to have any comments or questions.
Thanks a lot, Kristen, for the excellent talk, really informative. Yeah, any questions we have? Both in person and online. So while the others are thinking, I can start. So I think I really find the vision really cool. Like we have a personal assistant, and in the future that can just give feedback. But I feel like the current line of work is still just kind of post hoc commentary, right? What do you think is missing towards that real-time interactions? In the sense that, for example, if the person is kicking the ball and then he corrected himself based on the feedback he get first, but then maybe the step is still too small and he need to make a bigger step even. And what do you think about those kind of feedback, like grounded to the action, but in an interactive type of way?
Yeah, for sure. No, I think you're hitting on a really great challenge. To, the fullest version of this, realizing that kind of vision in the beginning will require, iteration, interaction, and in particular, learning. So we've started here looking at how you can give actionable feedback, but okay, just like you're saying, what's the action taken, and then how does the coaching or feedback progress from there? So could be a very strong notion of memory that's required for these video models, as well as the potential to have kind of personalization or style preference, so if we go, taking this to the limit, understanding how to coach well is not just about knowing the material really well, it's also about understanding personality and style of learning and things like that. And I think there's scope for that as we keep progressing, and it's a good way to, think about the challenges ahead. And you're right now, looking more in a kind of one shot or like one turn kind of manner to get us started for the expert commentary.
Yeah, it's cool. Yeah. Another question I had was related to 3D information, like what you showed about the future activity prediction, including where and also what object. So I guess for that line of work, one would require this kind of 3D information, right? But when it comes to 3D, as far as I understand, it's only like Ego-Exo and maybe the recent HD Epic dataset has 3D information, and most of the other video dataset don't have this. And also it's in general quite sparse, the 3D data, right? So what do you think? Would the 3D data really be needed? And what would be the most useful scenarios for using or benefiting like the task? Yeah.
Yeah, I mean, I think it absolutely is needed. And so, the data sets you mentioned are good kind of additions to like allow these kind of studies to start to happen. So is more needed? Yeah, I think that is, of course, always true. I think that, these resources just allow us to do those kind of checks. And I don't think, okay, so like there's one thing of, yeah, I think there's, the view of saying, well, like how rare and specialized will be, access to these kind of measurements in the world. I don't think it's that far away. So, the research device, the research collection platform we use called ARIA it's developed at Meta. It, it has these glasses with 2 SLAM cameras, RGB camera, gaze and other sensors and so on. And, that system with kind of the services provided with it, just state-of-the-art SLAM, are quite effective and for camera localization. So even though many of us, and me included, had not been, going there, I guess, for activity understanding anyway, I think we're not far off with today's best techniques combined with plus or minus today's best devices to say like, oh yeah, we don't have to think of it as, 2D pixel frames. We can register what we're getting in terms of the 3D environment. And to be clear, although I didn't explain it in full in this talk, we're not processing point clouds to do this representation. The key thing is the reconstructed camera pose and detection of objects, and placing them in 3D.
Yeah. Cool. Thank you. Do we have any other questions? Okay. Yeah, we have one from online. So the question is posted in chat. Should I read it aloud?
Sure. Yeah, I'm not seeing it here. Be glad if you can read it.
So basically the question is, the videos for training in sports often show a person alone interacting with inanimated objects, basketball or net. Would the fine-grained video understanding also work if the person is playing against other players?
Yeah. I think this is certainly another great dimension that adds complexity. So in Ego-Exo4D data-wise, it's specifically single actor. So there are other people around but they're not really part of the central activity. And so it's single actor. And yeah, it's really interesting to think of multi-person interaction, in particular like team sports, as a great one. I think there's just different dimensions of skill that you'll get. So, you know, putting my sports hat on, you know, for the single actor, it's about kind of things like dexterity and skill and motion and you know, tactical quality. And then for the multiplayer, it'll be things like exactly how the game is played and, you know, vision of the field, that kind of thing. Of course, there's room for computer vision to do things on both. I've seen limited work. So I think I was looking recently at a paper, I believe the title was called Logo, and I won't remember the authors off the top of my head, but one example, like looking at multi-person sports like synchronized swimming, to start reasoning about, you know, the mutual positions and maybe poses of the people doing. So yeah, definitely another dimension that's interesting here.
We have another question. So thanks for the great talk. Is this Ego-Exo set up a scalable way to collect internet scale 3D point cloud data for 3D representation learning?
Yeah, so I think, right, so could Ego-Exo become internet scale? The main hurdle for scaling up Ego-Exo4D is because of the high quality of the time synchronization across the cameras and the calibration. You know, it involves like a rig and a setup, you know, and we've kind of published the process to do that, and, you know, the software and so on, so that it could be replicated and scaled up in other environments. But, you know, compared to, like, it has that much heavier, like that is the heaviness of the collection that will make it scale more slowly than things that just involve single camera, you know, on the go. But, you know, I think the hope here is that by doing that legwork, establishing it, you know, we wanted it to be regular and consistent across the 15 different sites where we were collecting, and replicable and like reset-upable day to day by different coordinators and so on. So I think we've done some groundwork there that hopefully does help in terms of reproducing. You know, are we going to see internet scale tomorrow? I'm afraid not, but I would love to see, you know, others who are interested in the data, and, you know, whether in that exact form or some other, scale up the resources in this way.
Yeah. Thanks a lot. Yeah, I think that was the question we have so far. So thanks a lot, Kristen, for joining us in the morning time and giving this great talk. And we will post it online so that more people will have access to it, of course.
Okay.
And
Yeah, sounds great. Thanks for having me. Thanks, everyone.